Bismillahirrahmanirrahim. Welcome students to the online lecture of digital logic design. In the today's lecture, we will discuss the Boolean functions. In the last lecture, we discussed the basis of the Boolean algebra. In the current lecture, we will be discussing the Boolean functions. This part of the lecture belongs to the course learning outcome 2. First, we will discuss the few basic properties regarding the functions, Boolean functions. First is the operator precedence. As you know, in most of the arithmetic you have been doing since your childhood, you always follow certain rules to solve any given equation. First, you always solve the parentheses, then you have the first as divide has the first precedence, then the multiplication. So similarly, when you are doing the Boolean algebra, you also have the similar thing here. The precedence here in such a way that the first is the parenthesis, the small brackets. Second is the not or the complement operator, then the and operator, and then the or operator. Suppose we have an example of this one. In this, what we will do is that first we will see that there is no parenthesis involved in this one. So we will separately solve each of them. So first, what we will do here is that we will first take y complement, because the second preference is of the not operation. So first we will take the y complement, and then we will perform this operation, x dot y. Then this is our second operation, and in the last one, what we will do, we will or this. So we will solve in this way. Similarly, for the next example, in the next example, you have seen that there is a parenthesis involved in it. So first we will need to solve this or evaluate this parenthesis. The parameters involved in it are this one. So first we need to solve this one. First is x and y. Then we will OR it with the z. Once we have done this, then we will take its complement. So whenever the parenthesis is involved, we will first evaluate the parenthesis, and then we will perform the other operation. Like in this case, it was the second operation was the not operation. Now we will discuss the Boolean functions. So far we have done the Boolean operators or the binary operators. Now we will be discussing the Boolean functions. In a Boolean function is an you can say an algebra that deals with the binary variables and different logic operations. It will involve few binary variables. Just like x and y, we have discussed these in the examples. So we will have two or more than two binary operators like x and y. Then we will have some operators like or and, which are also the binary operator. Then we have a unary operators like not, which is the complement one, and we may also have some parentheses. So just we have written few examples of different Boolean functions here. Each Boolean function is representing here a different thing. The first is the basically the AND of three terms x, y, and z complement. While the second one is the second function f2 is represented as the OR of two statements. One is the x1 and the second is y complement z. Similarly, the third statement, the third function is the OR of three different terms. Similarly, we also have a fourth of this one. What we are aiming here is that we would like to reduce or optimize these function. Generally, we optimize these function in two different ways, or with respect to two different ways. One is with the area, and the other is according to the speed. Most of the focus on this course will be on the reducing the area term. so that how we can reduce the area. By area we mean that the more the number of gates we use, the more of number of area it will acquire on a given IC or a given chip. So we would always like to reduce the number of gates involved in this. So how can we do that? We will be using the Boolean algebra concepts which we discussed in the last lecture to minimize these functions. First, if we just draw the truth table of it, because we have seen that in all these four examples, we have a three variable system x, y, and z. And x, y, z belongs to the binary variable, so they can have a value of either 0 or 1. So, if you have these three variables, you can you know that we have done in the last lectures that it will give us 8 different combinations of input. So we will first write these 8 combinations here. First one, second one, third, fourth, fifth, sixth, seventh, up to 8. So we have written here all these combinations. And now what we will do is we will be calculating the terms here, like the first function f1, then we will be calculating f2, then f3, and f4. For f1, when we are calculating, is that we have all the terms available, x and y is available, and we have to take the z complement and just then add and all the terms. We know that for the AND operation, it will only give a value of 1 when all the values are equal to 1. So in this case, we have two values, 0. This case we have a 0. This case we have a 0. Similarly here, similarly here. So if you see that only there is a 1 because there is a z complement here. So only at this place we will get 1. Otherwise, for all the rest combination, we will get a 0 result. So this is the way how we express a Boolean function in terms of a truth table. So this is a f1 represents the truth table for a Boolean function f1. Similarly, we will calculate the f2. In the f2, what we will do is we first going to solve this y complement and z, and then we will OR this thing with the x1, and we will calculate the f2. And similarly, we solve that we now, because we are ORing these terms, so it means that if either of them are 1, we will get a 1 in the output. So f2 we will get 1 here, and in the last 4 terms we will get 1. Similarly, we will be solving the f3 and the f4 one. This involves f3 involves 3 terms, while the f4 has 2 terms. So both of their truth table are given here. So we just need to calculate all these combination, and or the final result we will get the f3 and the f4 terms. You can see that the f3 and f4 are different from the equation side. It has different terms and it has different term, but the end results of both of them are the same, f3 and f4. The final result is for the both of them are same. So basically f3 and f4 are representing the same function here, because their values or the output result is the same. So f3 and f4 have the same function. Now we will try to implement some of these functions on a hardware using some gates, basic logic gates. We have discussed 3 different types of gates so far. One is the OR operation, second is the AND gate, and third is the NOT or the complement one. So if we need to represent this equation, a function f2, which is represented as x plus y complement z. So first we need to take the complement of y. So here we are taking the complement of y. And then its result is AND with the z term here. So it will give us z into y complement. Z into y complement we will get here, and we will get being x here. So when we will OR them using this OR gate, we will get the f2 function. So in this way we write all the gates that are logic gates that are involved in it. So we have basically 1, 2, and 3 gates involved in representing this. This is say 1, this is 2, and this is 3. So 3 logic gates are involved in representing this function. Now we will try to draw the circuit diagram for the function f3. In the f3 we had 3 different terms. First, what we need is we need to calculate the complement terms. So we have a complement here of x complement, y complement. It's used again. So we need to calculate the complement of x and y. So what we do is we first take the complement x here and the complement of y here. We write the inputs x here, y here, and z here. Now the next thing is that first the 3 terms are AND here, and then the result is OR with the other 2 terms. So first what we do is we perform the AND operation for this one, and this one. We need to perform the AND operation here. So look at this. If you look at this first AND gate here, what is it's performing? Its input are because we were getting the x complement here, and we are getting the y complement here. So this is x complement, y complement, and this is the z here. So here what we are getting is x complement, y complement, and z. This. For the next one, we have for the next AND gate, it's x complement, y, and z. So this is the x complement term here, this is the y term coming here, and this is the z. So this is basically x complement, y, z. And the last AND gate, it has 2 inputs, x into y complement. So this is the x1, and this is the y1, y complement, because we are using the y complement, so this is the y complement here. So this is x into y complement. So now what we need to do is now we need to OR all these terms. So what we do is we use a OR gate to OR all these 3 terms, first, second, and third. So it will give us the function result of the function f3 here. So in this way, if you look at them, that how many gates are involved? 1, 2, 3, 4, 5, 6. So we needed total 6 logic gates to perform this operation of function equivalent to function f3. Now what we will do is we will now represent a circuit diagram for the last one, the f4 one. For the f4 one, we have x into y complement plus or x complement z. This represents the OR operation here. So we will have this term here. This is representing the x into y complement, and this is representing the x into z. So if we OR both of them, we will get the result of f4. As we have seen that in the last slide, we said that because f3 and f4 produces the same results, so both of the functions are same. But if you look at the implementation, then you can clearly see that f4 is more economical, because in f4 we are using total of 1, 2, 3, 4, and 5 gates. We are representing a 1 less gate than the f3. So f4 is more economical as compared to f3. To minimize any Boolean expression, what we do is we use the Boolean algebra things which we discussed in the last lecture. There are 2 or 3 terminologies used in it. One is the literal one, second is the term. The meaning of the literal here is that any single term like x or single variable like x into or x complement or y into y complement is called the literal, while the combination of some or you can say the AND of the some different variables are is jointly known as the term. Suppose we from the last one what we have just discussed, we had a function f complement x complement y complement z plus x complement y z plus x y complement. This each separate term x y, whether it's complemented or uncomplemented, it is called the literal, and this whole thing is known as the term. So for this example, we have total of three terms here, and we will count the number of literals 1 2 3 4 5 6 7 8. So we have 8 literals here. So whenever we are minimizing or optimizing any Boolean function, we generally tend to optimize them using or in terms of literals or the whole term. So we will be using these terminologies throughout the minimization process. And as you have seen in the last slide too, if this term or this function's terms are reduced or the literals are reduced, that will always result in reduced number of gates, which will require reduced hardware and reduced equipment. Now we will discuss a few examples of the minimization. Actually, all these minimization problems are related to the Boolean algebra topic, which we discussed in the last lecture. Suppose we have a Boolean function like this one, and we can represent it in this way from the distributive law. It is very clear that you can see that the first term comes here, that x into x complement, and we have already defined that if we could take the AND of these terms x into x complement, it will always result in 0. So if we OR it with any other term, it will result in the same term. So it will result in the xy. So it means that if we have given a function like this one, we can reduce it or optimize it in this form, and both of them, this and this, will always have the same result. So instead of using this one, we will use this one, because if you try to realize its hardware, it will involve first a NOT operation, then it will OR with this y term, and then it will end with this term. So it will require at least 3 logic gates. But on the other hand, you can see that if we minimize it, it is only represented in a single gate, that is OR AND operation. So similarly, we again have this function here, x plus x complement into y. From the distributive law, we can expand it in this way. If we expand it in this way, you can see that this term is always equal to logic level 1. So either this will be 1 or either this will be 1 all the time. So its end result will be 1. So we can just AND it with the x or y. So the final result will be again x or y. Again, you can see that we are able to minimize or reduce the number of gates involved in this operation. The results remain the same. The result of this one and this one will be the same, but we have managed to reduce the number of literals here. Similarly, say if we have a Boolean function like this one, if we expand it in like this way, you can see that you can always perform certain operation using the postulates and theorems which we discussed. That you can take something common from all these terms, and the remaining one could give you a different result. So what they have done this, that you know that for this operation the end result would be 0. So for the remaining 3 if we just take the x common here, it will result in this term. It's basically the OR of these 3 terms, and we have already defined that that if we OR these 2 terms, it will always result in 1. So 1 OR with 1 will again result in 1, and anything that will end with one will result the same number again or same variable again, so it will again result in x. So you can see that we have there were multiple terms involved in it, 1 2 3 4 terms, and it had 1 2 3 4 5 6 7 literals. We are able to now minimize it into a single representation of just x. So in hardware, when we will be utilizing this thing, it will help us a lot in reducing the hardware size. Now we will do certain other examples. Suppose we have a Boolean function like this one here. What we do is we can see that we can take this x complement z term common from the first two terms, so which will result in y complement plus y, and we have seen that it is equal to 1. So the final result is this one. So again, we have managed to reduce the number of terms and both the number of literals here. Say we have another example like this one. There are a number of ways to reduce or minimize any given Boolean function in terms of literals and the terms. We can have to utilize the different postulates and theorems of the Boolean algebra in this regard. If you see this term, probably you won't see a very straightforward method to minimizing it. But if you carefully see that, you can always apply various techniques or theorems in it, like this one. What we have done is that in the last term there is no involvement of the x term. So what we could do is we could always add this term because its result is always equal to 1. So we can add this expression x or x complement, and if you multiply it with this one, we will get, and with this one we will get these two terms. Now if you can see these two terms, we can take the x and y common here and x complement z common here. So resultant here will be equal to 1 plus z, and this is 1 plus y. And we know that if you are adding any term with the 1, it will always give you the result of 1. So it is equal to xy, and this is x complement z. So in this way we were able to reduce it. So it's always not the straightforward thing. Sometimes you have to apply the different theorems and postulate that you have discussed to reduce any given Boolean function. And it's also not a unique way. Maybe a different user could follow a different path to solve this thing. So there are many ways possible to reduce this Boolean function. Everyone may use or apply a different track to achieve the minimization process. Say now this is the last example. We have to now minimize this thing. We have directly written the result here. If you clearly see that and try to pause for a few minutes and just try to answer it yourself, that how we are able to get this result. Actually, this result has been achieved from the duality principle, because you've seen that this expression and this expression are the dual of each other. So both of the expression are valid. So similarly, both of the result would also be valid. So what we have done is we have first taken the dual of it has here, and then what we do is then we have taken the dual of this result here, which resulted in this one. Now we will discuss a little bit about the De Morgan's law. We have discussed it before in the table in the last lecture. Now we will be trying to understand the De Morgan's law with respect to more than two variables involved, because what we have seen is that De Morgan's law was only for the two variables, say x and y. Now we are introducing some other variables in it, and then we will see that how we can use the De Morgan's law. Actually, De Morgan's law is utilized in the complement operation of the function f. We have discussed the function f. In the function f, we have seen many examples in which we are given a certain Boolean function and we write a truth table for that. And for the truth table, we have seen that for any given location, we will get at certain specific location we will get ones, and for the other location we will get a zero. So if we want to take the complement from say directly from the truth table, what we do is we take the all those component in which the result is zero. So for a function whose values is 1 on say certain location, say 2, 3 and 4, for the all other location will give us it's the complement one. So how can we, first we will see that how we can take the complement using these mathematical expression. Say now we have a 3 variable system A, B and C. And we have to take the complement of that. What we do is first we say that B plus C is equal to X. So we will write in place of B and C, we will write X. So it will make it like it's a 2 variable system. And you know that from the De Morgan's law, if you solve this thing, it is equivalent to A complement into X complement. And now we again put back the value here, B plus C complement here. You know that B plus C complement will result again in B complement into C complement, and from the associative law you can see that the final result is equal to A complement B complement into C complement. So from the De Morgan's law for the 3 input system is that if we have a 3 variable system A or B or C and the whole complement is given, its final result is given as A complement and B complement and C complement. Similarly, for the other part of the De Morgan's law, we can apply the same thing here, that if we have done like this one for the first one, and for the second one, if all the operations are and the whole result is complemented, then the final result will be equal to A complement, B complement, or C complement or D complement up till the last complement. So in this way we can apply the second part of the De Morgan's law. Its derivation is similar to the one in this one. The complement of a function can also be obtained by another method, which is a much easier one. It involves interchanging the and the or operators and then complementing each literal. So this is an alternative method to calculate the complement of any given Boolean function. Say we have 2 Boolean function here. First we will solve the first one. In the first one, if we take the complement of this function, we can always call it this whole term equal to A and this whole term equal to B. So the resultant would be equal to A complement and B complement. So and then if we take the put the value of A here, which is equal to X A complement Y into Z complement, then you know that from the De Morgan's law we can write it as like this. It will become this A complement complement. It will make it A or the simple X. This will become as the complement of the second operator Y, so it will become Y. And third is the Z or the C complement. Complement means double complement, so it will result again in the Z. Similarly, for the next term, we will performing the same thing. We will put the values, take the whole complement. This is equal to taking the X double complement, which will result again in the X. We will then again be taking the complement of Y twice, which will again result in simpler Y. And then we need to complement the Z, which will result in the Z complement. So in this way, we apply the De Morgan's law, which we discussed in the last slide, to calculate the complement of the function f1. Now we are calculating the complement of the functions. And for similarly for the second function, say second function here is represented as f2 complement. So what we do here is, this is the whole equation for the f2. We take the whole complement here. So again, what you can do is you can represent this whole term here as equal to certain variables. Say you can represent it as this whole term here as say A. Then this is X complement and this is A complement. And so how you can then solve it? Then you put the value of A here and then you take the complement, and because it involves 2 terms here, so each term will also get a complementary term here, like this one and like this one. And after that, what you know, that because it's the complement term here, so when you express it in applying the De Morgan's law again, this will result in y complement. Complement means double complement, so it will cancel out and you will get y here, or z complement complement, which will again represent the z here. And similarly this will be ending with this term, again it will become complement of y complement here, or z complement here. So this is the result for the complement of f2 function. We have done here is we have utilized the De Morgan's law, which we have discussed in the last slide. And now we will discuss the more easier operation of taking the complement. You can always take the complement from this one, but we in the last slide we have discussed an alternate method to calculate the complement. Now we will be calculating, say, the function f1 with from the other equivalent. What we need to do is we need to take the dual of the function, and then we have to complement each letter. Say this is the f1 here. So what we do is that first we take the dual. What in the dual, what we do is we interchange the and or gates and one with the zeros. So this is and here, this is the or operation, this is the and operation here. So what we need to do is we first need to convert these and gate into the or ones and the or into the add ones. So we have changed this into the or ones now, and this into the and one, and these are also now represented in the form of or gates. And now in the last step, what we need to do is we need to take the complement of each literal. So we take the complement of this x complement. Complement will result in x, this will result in y complement, this will result in z. Similarly, this will represent x, this y, and this is z complement. And now if you look at this f function, it's the same as this one. So you can always apply both of these procedures to take complement of any given function. Probably this is the much easier one because it involves the dual and then the complement of each literal. So it's probably more easy, but it's up to you. You can always apply both of them. Both of them will always result the same thing. Kindly do read these pages from the book. Thank you.